right, so let me get connected here and we'll be in business. Looks like I'm connected. Okay, yeah, I must be because it says introduction. Okay, so let's talk about correlation and regression today. We're going to change gears a little bit here. We're going to talk about something that is an analysis of variance for the first time since January. And it's almost the end of March. Doesn't look like the end of March. What's it look like outside? It looks like a nightmare.
It feels like Newfoundland.
It feels like we're back in Newfoundland. It does. Where it just snows all the time and then suddenly it isn't and then it's just a whole bunch of water. Anyway, everything we've talked about so far has dealt with differences between groups, right? And, mean, group mean differences. That's what we've been looking at the entire time we've been doing this course, really. Right? So we've been looking at t-tests, f-tests, z-tests even early on. Those are all different statistical tests we've looked at. But they're all about mean differences. You can always look at this as a relationship between a relationship between an independent and a dependent variable. Right? You can always do that. So if you think about this, it's especially easy to see with a continuous variable or a variable that has many levels. So typically our independent variables, at least so far in this class, have always been, group 1 has 3 levels or something like that. Or, the quiz example, we had A with 4 levels and B with 3 levels, right? Here I'm talking about something with many, many, many levels or perhaps an infinite number of levels. It's easier to see how we can talk about this as a relationship between two variables. So I'm going to show you just and these data aren't real. If only it was so. So this is a scatter plot that I made up, and I just put numbers in, and I said this is IQ, and that's your income in thousands of dollars. I made that up. Your yearly income. These are completely made up. There's no way it's that tight. There is a relationship, and it's about 0.6 between IQ and your salary. That's a real thing. All the people who say IQ doesn't measure anything are just idiots who have low IQs. Because I'm afraid that they have low. I'm serious. I have no idea. Why are everybody so afraid of it? It's like it measures a thing and it correlates with a thing. Anyway, it's not that tough. So I just made this up, and then again, you can see I just did this for myself, just as series 1. I just put these values into, I think it was, that looks like it comes from the Mac OS program Numbers. That's probably what I used, and I just said make a scatter plot. But you can actually see here that if we had IQ points here and then income here, you can see the relationship here. So instead of just being like, whatever we want to call it, let's say the independent variable, not that we manipulated anything here. But if we talk about one of these as an independent variable, it's got a lot of levels. Let's put that over there. Scatter plot obviously is a useful EDA tool. And I think I've talked about it in that, in relation to exploratory data analysis. But it's also just useful. It's a way to look at data. So what if we want to do some comparisons? Like that number should be the same if you're measuring your income in Canadian dollars or euros, right? Or it's an obscure currency. I don't know. Thai baht. How about that? So you're measuring. Doesn't matter, but it shouldn't matter, should it? And it shouldn't matter actually. Some of these IQ tests all measure the same thing. It shouldn't matter if you're using the Wechsler Adult Intelligence Scale or the Raven Progressive Matrices Scale, if they're measuring the same thing. That's a little more iffy, but definitely it's the case that if I make a certain amount of money every year, but if I convert that into American money, it's still the same amount of money. It's got a different number. So we should be able to standardize this kind of thing, these relationships, and that's of course what correlation's all about. So the first thing you could do, we've been talking, the whole course has really been about variance. We could rename the course Variance. Isn't it interesting? No, we wouldn't do that. That would be going backwards. But it's all about variance. Oh, look at that. It's a formula. Now don't be frightened by this. Look at it as a variance formula. And you can say, oh, I see what this is. Because look, on the bottom we got big N minus 1. That's the number of observations minus 1. Oh, that looks like a variance. The top has deviations from a mean times, deviations from a mean from another variable, x and y. This what the covariance does is it allows you to look at how much variance is shared between two variables, how much overlap there is between two variables. And you can see here, I think, that if both x and y were measuring the same thing, so if it was height in centimeters and height in inches, right, we just get variance. Or height in centimeters and height in centimeters. Let's make it like just, so it's the same numbers. We just get a variance there. So these are x, y pairs, and there's a shared variance there. It's called the covariance. So this is going to measure the degree to which two variables vary together or co-vary. Or if you think of variance as a thing, which I think is a little easier now than it probably was at the beginning of the course. If you think of variance as a thing, which is an odd thing to imagine, but if you think of variance as a thing, there is variance of x and variance of y, and they overlap. It's the same variance. It's the covariance, hence the name. By the way, I'm perfectly fine with people using the rise of the word hence. People have been using that a lot. It's great. Too many people say hence why. It's redundant. When you say hence, the y's in there. It's driving me crazy. Oh, look, people know a word. Oh, they're using it incorrectly. So if deviations from x and y go in the same direction, from x bar and y bar, then you should get a positive covariance. So the difference here is that covariance could be negative. Regular variance can't be negative, because it's squared, right? This isn't squared because we have two different sets of numbers, the x's and the y's. So if as x goes up, y goes down, we're going to get a negative value here. If as x goes up, y goes up, or as x goes down, y goes down, we get a positive value. All the sign is telling us about, of course, is the direction of the relationship. You can see how this is going to lead to correlation, because I know you all know that about correlations already. So if deviations from x bar and y bar go in the same direction, we get a positive value. If they go in the opposite directions, we get a negative value. Okay. The problem with covariance there, and this is why I backtracked and I said it wouldn't work with, it's not the same numbers with variance, height in inches and height in centimeters. It actually wouldn't work. It should be the case that if we measure height in centimeters and height in inches, we get a perfect relationship, or if we measure height in, income in dollars and income in euros, get the same relationship. We have to get a standard measure of association here. We're getting there, but those variance numbers are going to depend on the actual, numbers themselves. So we want to standardize covariance. So scales don't matter. It shouldn't matter if you're measuring temperature in centimeters. Well, that would matter because you can't measure temperature in centimeters of mercury in a thermometer. In centigrade, Celsius then, and Fahrenheit, it shouldn't matter. So the problem here is that covariance actually depends on the numbers themselves, as I said, obviously, but it depends on sub s sub x and s sub y. So if we have a bigger variance or bigger deviation, we're going to get a bigger covariance. And when I say the number's going to be bigger, but it doesn't mean the amount of overlap is bigger, does it? We want something that's going to standardize that. I almost put that over here because I thought for a second that was my coffee. This is how bad. See, I don't think people understand it that way. This is my coffee. This is not technically. You might wonder how I ride a bicycle. Really well. That's how I ride a bicycle. Depends on those things. Let's divide by them. That's what we would do, right? If we're going to standardize by those, if it depends on those things, let's divide by those things. That should fix it. And then it shouldn't matter what our scale is. So let's do that. And we end up with the Pearson R. And the Pearson R is the covariance of x and y divided by s sub x times s sub y. It's actually, the Pearson R actually is a longer name. It's called the Pearson product moment correlation coefficient. Well, product moment, here's the product right there. There's a product, right? You multiply two things, there's a product. It's called a product. Remember that from math? Yeah, I saw it. Victoria nodded her head. I saw that. That's good. You remembered something from high school math. That's excellent. Okay. It's always nice when people remember things from high school math.
That's like grade 4.
Grade 4, you talk about product. Sure, could be earlier. I just don't know how they teach anything anymore. So, 'cause I think you just show up to high school and they give you a diploma, right? So,
Pretty much.
pretty much, yeah. so if covariance of x and y, that's the absolute value of the covariance. That's those two lines mean. So just we're ignoring the sign. If that equals s of x, s sub y, that means that the absolute value of r is 1. You have a perfect relationship. So in fact, if you had height in centimeters and height in inches, you're going to get 1 if you do this calculation. If you have income in euros and income in Vietnamese dong, I know lots of units of money. I have all kinds of really weird knowledge that is completely useless. It's good in trivia games. Like, it's really good for that. When I was like 8, I knew the flag of every country in the world because I was a weird kid. Shouldn't think that's good. It's weird. So we get a correlation of 1, that'd be great. Right? We know that then we have the same variable. The sign of r still just tells the direction. So if the sign is positive, as one goes up, the other one goes up, so it's an uphill. If it's the sign is negative, as one goes up, the other one goes down. It's going down. Okay. R can only be between -1 and +1. I'm going to tell you something right now. I'm going to ask a question on the final quiz. And the question is going to be, which of the following are the largest correlation? And one of them I'm going to give you is going to be greater than 1. It's going to be 1.2. I'm going to tell you the numbers. It's going to be 1.2. And some of you are going to write down that that's the largest correlation. And you're wrong, because it can't be. It can't be greater than 1. Yes, Ellen?
This might be really stupid.
Don't say that. It
But
might be, but let's pretend it's a great question.
Okay, so I'm pretending it's a great question. The absolute R,
Yep.
that means if there is a negative value, we're gonna take it out, right?
That's right.
So how are we gonna get a value which is like between negative
Oh, right.
and
Well,
positive 1?
Just this doesn't have the absolute value signs.
Oh, okay.
Yeah, you're saying the absolute value. If we took the absolute value of R, it would equal 1 in this case here. Right. So this is making it more general. So if we had covariance of x and y equals s of x times s of y, that would mean it would have to be positive.
Okay.
Yeah. Because covariance can be positive or negative, I just did that in this case. Make sense?
Yeah.
Okay, good. So yeah, I'm going to give you this question. I'm going to ask you which of the correlations is the biggest. And one of you at least will pick like 1.2. And I'm going to make that the value, 1.2. I'm telling you right now I'm going to do this. Don't do that. It's not a correlation. You look at that and go, well, that can't be that can't be the biggest one because it's not a correlation. It's a mistake. It can't be greater than 1. It is impossible. Look at that. How could that ever be greater than 1? Just look at this. It can't be. It is impossible. It's not like, remember when I said the f can never be greater than 1, and then we go, well, or less than 1, it's like, yeah, that happens sometimes. This can't happen. It is literally mathematically impossible for it to happen. No matter what assumptions you violate, it will always be the case that it will be between 1 and -1. So the absolute value of R indicates the size of the relationship. So a correlation of -7 is bigger than a correlation of +0.4. Okay. And a correlation of 1.2 isn't a correlation, it's a mistake. It's wrong. It's not even, it's actually, there's an expression we use in science sometimes, not even wrong. Saying you got a correlation of 1.2 is not even wrong. It can't be the case. That's like saying, what'd you get from your correlation? You go, I don't know, chairs. It can't happen.
You should be the chairman.
Chairman of what? I was the chair of the psychology department for 7 years. It was a nightmare.
You should be the chairman.
Right, only straight lines. So we have to have a relationship between two variables. Let's draw one here. And we had our income in IQ1, and it was, sort of like that. But if we had a relationship, how about a dose response curve? A lot of you people here have taken neuropharmacology from me, and if you haven't, you should take it next year. It's a great class. A lot of dose response curves look like this. Right? Low dose, very little effect. Mid dose, awesome, you're having a great time. You've had like 4 drinks. You're dancing perhaps. Maybe you're singing karaoke, things you would normally not do, except that there's alcohol involved. Then you hit about 8 drinks and you're pretty relaxed again. Passed out. If you had a perfect, all along that line, and we got a correlation coefficient of 0, it would show up as 0 with this. Because this only works with straight lines. Okay. There is a way to find out the correlation here. If you had an upside down parabola like that, totally doable. It's theoretically it works the same way as what we're talking about today. It's just that it doesn't work. It's not linear. That's all. So you have to know the shape of the curve first. This is assuming the shape of the curve when we talk about this stuff today. And also with multiple regression, is going to be all straight lines. And if it's not, that messes everything up. However, if we violate this assumption of straight lines, that actually can make it so we get a covariance of 0. We can get a covariance greater than 1. But we could end up with something like, we get a covariance of 0 with that parabola. We would get 0. And we would look at it and go, all the lines, all dots fall in a line. Doesn't matter. You'd still get 0. Like I said, there are ways to deal with it. The problem is you have to be able to look at your data and go, I know what that function is. And for a lot of us, we haven't done anything with functions since, well, maybe grade 12, right? In high school, you're dealing with functions. But
Out of that class.
well, a lot of people would be like that, right? Because a lot of people don't take, this is one of the I have a real problem with a lot of people, as you probably know. But I have a real problem that a lot of times like guidance counselors don't understand what programs actually have in them, which is bizarre to me. So like, they'll say things, I remember in fact, my high school guidance counselor, who was great, and I said, when I was picking my classes for my final year, I said, I think I should take all the math. I should take calculus and functions and algebra. And she said, that'll be really good practice because and she had a psychology degree. She said, if you wanted to go into psychology, that'll be good practice. You can do a lot of math in psychology. She knew, but the number of people I hear that sort of join our program and they say, I haven't done math since I was 14. Who told you you didn't need math? You always need math. Math is good. It makes you a better person. But maybe you can't recognize that. You know what you do? You go to the math department and you go, hey, Edna, what's the shape? What curve is that? And Edna will look at you and go, that's a parabola. And you walk away. You're happy. Everybody wins. Maybe you give her an acknowledgement of your paper. What I'm saying is that if it's a funny shaped curve, it's like, I don't know what funny shape that is. Right? And someone like Edna James, for example, I'm sure, could look at it. I mean, I could look at it probably and say, I know what that is, but not everybody can. It's a straight line, it's easy. It'd be great if we could predict y from x. It'd be great if I had a tied up shoe. This thing needs me breaking my leg. Again. Okay. 5 years ago, right about now. Yep. Oh, and also all of society stopped. There was that 1 week period where I didn't have to go to work and everyone else did, and I was like, this is awesome. I'm going to work from home. I can work, and it was all set up. I was going to teach my classes from home. Everything was good. And then, so I never got my little reprieve. Everybody worked from home. So I blame COVID for being annoying. Not for the deaths. Oh, I'll blame it for that. But what really pissed me off was I didn't get to have extra time off when other people did. That's not the only thing that was bad about COVID. Okay. If we could predict y from x, that'd be awesome. Right? It's something that, it's got a really nice intuitive appeal to be able to predict y from x. You look at a graph, it'd be nice to be able to go, oh, if your income is this is your education, or vice versa. So basically, if you draw a line through a scatter plot, I'm going to just I'm just going to make a scatter plot. Yeah. Here we go. So I'm just going to make a scatter plot. So let's do that. So I don't even know what these variables are, but I'm just going to put up some data. So really as funny as John thinks it is, but I appreciate the support. Okay, so there's some data. You can look at that and say, yeah, I see a positive relationship. In fact, I see probably it's a linear, straight line. I think we would all agree that we don't have some weird curve where we have to go on to the math department. Okay, so this is great. We can look at that. It'd be nice, again, as I said, if we could predict y from x. But there's an infinite number of lines I could draw. Right? Now, if I was to just do this, just eyeball this, that looks pretty good. Doesn't it? That looks good. Oh, here's another one. Maybe that's pretty good too. Well, what if we? Well, there's also this one. Those are all good lines compared to say that one. That's not a very good one, right? It's going the wrong way. We would all agree that that line going down because we have a positive relationship, that's a shitty solution to our problem. But it is a solution to our problem. How do we say that's a good one and that's a bad one? As I say here, we're going to use a least squared regression line. But you can see here there's an infinite number of lines even that are pretty good. Now there's the ultimate line to predict everything, but it's not useful. But the one that will have no error is we actually just connect all the dots. And doesn't matter, you can go to the math department, they don't know the function, the name of that function. That's useless to us. But it's actually 100% correct. Like there's no error if you just connect the dots. The problem is you have no degrees of freedom. Do you? All of the values are assigned by me. They're all arbitrarily assigned. Not arbitrarily, they're all fixed. We want something that preserves preserves the wrong word. We want something that will predict y from x, but have the least number of assumptions. Look at all the assumptions here. All of them are, if this is x, this is y. If this is x, this is y. That's not very useful. What would be nice is if we could just draw a line with an equation. And you all were taught equations of lines. Some of you, it was a long time ago, probably most of you it was a long time ago, but you were all taught that. That'd be better. And that's what we're going to do. We're going to get what's called a least squares regression line. So here's the idea. So we have 4 data points here. So those are y's. Those are the actual values. And then we have a predicted value. And that's y hat. A little, we call that a hat. I suppose in French it's not called y hat, it's probably called y circumflex. But we speak English. Yeah. So, y hat. I constantly meet colleagues or francophones who teach statistics. I always want to ask them, they call it, y circumflex or y chapeau. So, what we want to do, and then we have this is the y hat line with the y dots. We want to minimize these distances because those are mistakes. The distances from y to y is a mistake. It's a prediction error. Let's make those as small as possible. Does that everybody make sense of it? So you see sort of theoretically what we're doing? Okay. So let's minimize y minus y hat, and we're going to square it. Because obviously what's going to happen is if we just add them up, it's going to be 0. So we're going to try to minimize the sum of y minus y hat squared. And again, thinking back to your math, I'm not gonna have you have to do this, don't worry, but thinking back to your high school math, remember doing minima and maxima of functions? Yeah, some of you nodding, some of you saying no, but that's okay, because that's kind of advanced stuff. But those of you who remember doing it, remember it actually wasn't horribly complicated. It's something that's doable. You can find the minimum and the maximum of a function, and that's what we're going to do here. That's what, in essence, what happens here. And again, don't worry if you don't remember how to do that. I just brought it up because a lot of you will remember doing that and remember, oh yeah, I remember how to do that. It's not that hard. And also reminding you, again, that you probably thought to yourself, I will never use this again in my life. You are about to. So what you get is a prediction equation. And the prediction equation is y hat equals a plus bx. Predicted y equals the intercept plus the slope. Yes, I know. I know. You were taught y equals mx plus b. We all were. And then we all get to statistics, and they tell us that b isn't the same b, and now is an a, and there's no m. But it's functionally the same thing. Okay, so that's the intercept here. This is where x has no value. This is x equals 0, and then we get a slope. Look at how simple that is. That's a very simple kind of prediction model, and it's actually pretty easy to understand. We'll get it. We'll think about some real values in a second. Have you noticed I've not really told you how to calculate these things because no one does these by hand? I'll show you in a second some stuff, but no one does this by hand. You have to be out of your mind to do this by hand. People used to, because before about 1970, everybody was out of their mind. And there weren't calculators. Well, they existed. They were heavy mechanical units. You know? So how do we calculate B? We get the covariance of x and y, and we divide by the variance of x. So all the math in the background that does finding the minimum of y minus y hat ends up that you get that b is this, and a is y bar minus e times x bar. So if you have a, you can get b. Because if you have a, you can calculate y bar, you can calculate x bar, you can get b. If you have b, you can get a. So you only have to calculate one of them. And b is pretty easy because you already did a correlation, so you probably have these values. So if you were doing this by hand, it wouldn't be horrible. It's just that there's so many places to make mechanical errors. I remember actually doing these by hand. And I wasn't doing statistics pre-1970, but in my intro stats class when I was an undergrad, near the end of the course, we were doing these by hand. And there were so many places to make mechanical errors. Like so many, so very many. That's why you would use a computer. All right. What's this here? Okay. So A is the intercept, and that's where x equals 0 is not always a useful quantity. So where x equals 0, let's say we're predicting. I don't know, what are we going to predict? Oh, wait a minute. We're going to predict the number of cigarettes people smoke per day by the number of years they've been smoking. It's a linear relationship. It's positive. We would come up with something. So we're predicting cigarettes per day from number of years smoked. Okay. Well, number of years smoked, so it was 0, that's the intercept. But we're not, so there right there, that's a meaningless quantity, right? Because people who have been smoked for 0 years don't smoke. It's meaningless. What if we had something like we were predicting people's income based on their age? And again, there's a positive correlation there, because the older you get, the more chance you have, you've been around longer, you know more people, you've got more education, more experience, you get paid more, right? We'd get a value. We'd also probably get an intercept. And we could say, well, when people are 0 years old, they make this much money. That's meaningless. How many babies do you know that have careers? Very few. It's a small number. So again, it's a meaningless quantity. So it's very, like if we had a, let's erase my mess here, we'll just draw a line in. All right, so if we just drew a line in here, this is just predicting x from y, and we just get that. It's very tempting to interpret that origin point. It's very tempting to interpret the intercept. Or, let's say it goes like this. It's very tempting to say the base value for anybody, no matter what their level of whatever, is right here where it crosses the axis. We want, but it's not going to work. Not always. We also always want linear relationships. Only straight lines. Now, how do we know? Well, it's pretty easy to determine if we have straight lines, right? When you just do a scatter plot and look. And you should be able to look at that and go, that's not a straight line. Or, what's going on? I know there's a relationship here, but I got 0, but maybe your relationship looks like, a curve. Looks like that, you're not going to find it. Now, there's another way to do this, and it's just to look at what are called residuals. And this sounds like an extra step, and just for simple regression, it is an extra step. When we start talking about multiple regression next week, this becomes a lot more valuable. But if we look at a residual plot, they just look like this. We're going to plot the residuals. Residuals are just those prediction errors. Okay, we call them E for error, or y minus y hat, 0. And then we look at how much, this is the x value along this axis here. Just look at that. And if we see that it overpredicts as much as it underpredicts, it's fine. And there's no relationship between the x and the prediction error, we're good. However, if we saw something that looked more like this, like a parabola, you can say, oh, it overpredicts, it underpredicts, it overpredicts. Oh, it's a curve. So you can do that by looking at residual plots. The nice thing with residual plots is when you're using a regression procedure in, say, SPSS or PSYC or anything, you can just say, oh yeah, also give me residual plots. Okay. So that's the other way to do it, is to look at the residuals. That'll help you find out if you have a linear relationship or not. The covariance between x and E, in other words, between x and the residuals, you can actually calculate that. It should be 0. There should be no relationship between the value of x and the size of the prediction error, the size of the residual. Okay? So you can always just calculate that covariance if you felt like it. Don't go outside the range when you're interpreting this of the data themselves. So, and again, it's so tempting because you come up with a formula. You literally get a formula, right? So, if your formula was, let's say we were predicting so remember, the formula is always just y hat equals a plus bx. Let's make this a little concrete now. Let's say this is your salary equals some intercept plus some number of the slope times years of service. So in fact, that's how my salary is calculated. So there is a base number, we'll call that the intercept. And I'm going to make up some numbers because I can't remember how it's calculated. So these are made up numbers. Okay, so what I said here is that a salary would equal 120 plus 5 times the number of years of service. That's not it. I literally could look it up. And you can too. A collective agreement is a public document if you want it. And my name will be published soon about how much money I make in the paper. Because I'm apparently supposed to be embarrassed that I make a decent living. Anyway, what you could do though, is if this was the case, you could say, okay, how long have I worked here? I worked here for 20 years. Obviously this is wrong, because I don't make 2.25 a year, or whatever that would be. But 120 plus 5 times 20 would be 120 plus 100 would equal 220. Now again, I don't make $220,000 a year. I'm not important enough to make enough money. I'm not an administrator. But you can look at that and go, okay. And to make it a little more reasonable, it's probably, this value shouldn't be that high. It should be more like about 40. Okay. So anyway, you look at that, you say, oh boy, makes $220,000. I bet if he had worked here for 1,000 years, how much money would he make? It doesn't make any sense. You can't go outside the range. Or you can't say, well, what if, somebody had no years of service? Well, or negative. What if you had a negative number for years of service? There, that's even better. Yeah. So let's, because the numbers don't know where they come from. So let's say you've worked here negative 20 years. That would mean you owe the university $220,000 every year. That's, again, stupid. Makes no sense. You can't go outside the range that you collected the data on. And the range for this is 0 years of service up to whatever. It's more complicated than that, but it is just an equation. How do you figure out our salaries? So you just don't go outside the range, and it's very tempting to do that because you look at something like that and go, oh, I see, I can do that. Makes no sense. Questions on correlations? I know you've all dealt with correlations before, but I don't think you've dealt too much with regression. You don't talk about regression 21-2060? No? No, I didn't think so. Okay. So that's the new part today, is the prediction part. And all it is just turning turning a correlation into a formula for prediction. It's all it is. You want to ask something, Victoria, or you just doing this?
I do, but it's like with that example, it's more of an exponential growth because it's based and then like percentages each year.
Yeah, well, no, the way it actually works. Do you want to know the way it
my
actually
collective
works?
agreement for where I work is it's a certain percentage we go up each year from the previous base salary.
Yeah, it's more complicated than this because all the values change every year.
Yeah.
Right. The base, so that's the floor, and then the size of the steps, they change every year.
Yeah, so it's more like the exponential.
Well,
It's
yeah, it's
not quite.
yeah,
but
it's complicated. It's complicated. But in essence, that's what happens here. Is that it works something like this? That there's for each year of a contract, this is the base. And this is how much you get paid per step, so per salary step. I think I'm on step for my rank. I believe I'm on step 13. So I'm not actually on step 20. I've worked here 20 years, but I'm not on step 20. I don't think there is a step 20. It's complicated. And also, like, when I got here, my years of service weren't 0. They were 11. Like, it's complicated. Because that's the one place you can negotiate things. Give me credit for this stuff I did. Any questions? Other questions? Like I said, I know you've dealt with correlations before. You haven't dealt with regression before, but it's just an extension of the same thing. One of the things you're very tempted to do is when you see, and in this case it's true, that actually is a causal relationship. I am paid based on what the number of years of education, well, partly there, the number of years of service and the floor, basically the intercept. That's true. That's a completely valid thing. On the other hand, if we have years of education and income, years of education don't cause income. I believe somewhat. But education also income causes years of education. Right? Because if you have more money, you can afford to go to school longer. Yeah. So it doesn't, but it's very tempting to go, oh look, it says this plus this equals that. That means that's the way the world works. Don't do that. It's very tempting. And sometimes it's true. But usually it's not. Usually, remember, correlation is not causation. Just because it's written like this equals this plus this doesn't mean that it's causal. It just means that those two things go together. All right. Any questions on this stuff? Are you good? I think you're awesome. Okay, go home.